Good morning, guys. Today, you guys are going to learn about the 3 criteria to prove that triangles are similar. Now, we did something like this with triangles with congruence, but now we're talking about something completely different because obviously we're not trying to show that 2 triangles are the same size. We wanted to show that 2 triangles are proportional to each other. Okay, so I'm going to show you the first one. The first one is called the angle similarity rule. Angle similarity. This one's very straightforward. So here we have triangle ABC and triangle RST. And this lesson, though at least the first part of it, is mostly about notation. Do you know how to say it properly? And all of that stuff. So again, we're using the angle similarity theorem. And all it says is if you have 2 triangles and you need to prove or show that they're similar. So notice I did on purpose make triangle RST a little bit smaller. I actually don't need to know any of the sides. I need to know that two angles that correspond with each other in each triangle are similar. So if I gave you this picture and I ask, are these 2 triangles similar? Your answer is yes, because I know angle A is congruent to angle R and angle B is congruent to angle S. Then they're similar. Now, similarity, what we know that means is that the sides are proportional to each other, and we're actually going to use that in a minute. You learned about ratios and proportions back in middle school, so it's definitely not a new concept. But let's talk about how to write the similarity statement properly. We would say triangle ABC is similar to, so it's like the congruent symbol without the equal sign. It's just the wavy line. Triangle RST. Now I want to make sure I'm putting them in the right order because like congruence, things have to be corresponding, right? We know that angle A is congruent to angle R, so we can see here that I put A first and R first. They have to be in the same spot. You can see that with angle B and angle S. I know they're congruent, so I put B and S in the same spot. I put them in the middle in this case. And then, of course, I have angle C would be my last angle. Angle T, they correspond. C and T are in the last place. So again, I would ask you, are these 2 triangles similar? You see that 2 of their corresponding angles are congruent, and that's really all you need to know. Yes, these 2 triangles are similar. Okay, so that's the first theorem. The second theorem is actually a lot like, let me find a good example here in my book. Excuse me. A lot like a theorem that we did with congruence, but this one obviously is, again, we're not doing congruence, so it's a different theorem. So this one is a side. Again, this is a similarity theorem. Okay, so again, we can abbreviate. So this, of course, would be the AA theorem. And this would be, so we don't just write SSS for this one because we know we had side with congruence. We would call this the side similarity theorem, so you would want to put the little wiggly sign. Now, we didn't, if you remember, for congruence have an angle theorem with just the 2 angles. Like that wasn't a thing. You have to say that it's similar. Okay, so I'm trying to find a good example here. Oop. I'm trying to draw it so it looks halfway decent. Alright, so this is triangle. Let's see, this is ABC. And I'm going to attempt to draw this nicely. But we all know how that goes with me. So just kind of bear with me here. And then we have triangle. This one is DEF. So this time I'm not going to be told that any of the angles are congruent. I'm going to be given side measurements. So this one is 3, 5, and 4. And this other triangle is 7.5. 4.5. And 6, I believe. Yes, 6. Okay, so if I give you two triangles and we can't use the angle-angle similarity theorem, but I see that I'm given all of the side measures of all of the sides, I can check to see if they're proportional. And just to remind you, a proportional is just where you have equal ratios. So what I like to do is I like to use ratios from side to side. Now this one will ask something like it'll say in the directions, is triangle, ABC similar to triangle DEF? So they're telling you what sides match up with each other. Right? We talked about that in congruence. If I see AB is first and DE is first, then I know that AB and DE should correspond with each other. Now, obviously, they're not going to be the same size because we are doing a dilation. What we want to see is if they give me equivalent ratios. So 3 and 4.5, I would need to compare to each other. What is that ratio? But my job is not to just check that one. I have to see that they're all equal. BC and EF. So BC is 4 and EF is 6. So I would want to see the ratio for 4 over 6. Now please notice I'm putting triangle ABC on top and triangle DEF on bottom because that's how the similarity statement is written. If I had written it the other way with the DEF first, I would put that number on the top. And then of course the last two would be what, BC and EF, and I can see here that Nope, just said that wrong. Sorry. The AC, I was like, wait a minute, I've already done those two. And DF, there we go. AC is 5, and then of course DF here I can see is 5.7. So my job is to figure out whether or not these three ratios are equal to each other. Honestly, I'm just going to pick up my calculator. That's going to be the shortest way, and change them all to a decimal. Of course, there are different ways to do this. You can do cross multiplication. You can do conversion of decimals to fractions. But I see that the easiest way to do it normally is just to change this fraction into a decimal. So I'm going to pull up my calculator here. Let's see. So 3 divided by 4.5 is 0.6 repeating. And it's really important that you not just worry about, oh, it's 0.6, because sometimes you'll get some that are really close, some that may round to 0.6. They have to be exactly equal. So 4 over 6 also needs to be 0.6 repeating, and it is. And then let me check my last one, 5 divided by 7.5. So 0.6 repeating. So again, what I did is I just compared the three sets of sides that correspond with each other. I saw that whenever I compared them, which is again called a ratio, that they were all equal to each other. So since they're all equal to each other, that means they are proportional. Remember we wrote that word down yesterday, proportional. I had to think about it. Okay, so if they're all equal, they're proportional, which means that these triangles are similar to each other. Okay, so the side theorem for similarity, I actually have to show mathematically that the three sets of sides have equal ratios, or they're proportional. The last one, again, very, very similar to what we've done before. This one is the side angle side similarity theorem. Again, when we abbreviate this one, we can use SAS, but we have to put that little wavy line behind it because we're making sure the reader knows we're talking about proportionality or similarity and not about congruence. Sorry, I'm trying to find another good example here. Let us see. Okay, so this is a pretty simple one. This one's not too yucky. Here we have let's see, this is triangle JKL. And here we have a smaller triangle. This triangle is what? XYZ. And please don't ever go off of my drawings and, oh, they don't look proportional. Listen, I tried. We've had discussions about my drawings. Okay, so in this, I'm given that JK is 5, JL is 10, XY is 3, and XZ is 6. And then I'm also told that angle J is congruent to angle X. So we see here, if you remember from the congruence theorem, the angle is in between the sides for a reason. And that's what I have in this problem. If you look, I have a side, the angle in between, and the side for both of them, right? Side, the angle in between, and the side. The only difference is I now have to go one extra step to show that those numbers are proportional, just like I did back on the last example. So I can see here, obviously, that the 5 and the 3 are meant to correspond. So I would write 5 over my ratio for 5 over 3. 10 and 6 also correspond. So 10 over 6. Again, keep in mind that you have to be consistent. If I put JK on the top for the first one, I have to put JL on the top for the second one because they're coming from the same triangle. There is more than one correct way to write these proportions and ratios. Just be consistent. Again, I just want to know if these two are equal. You could very easily cross multiply on this one. That is another method. I usually don't use it on the previous example since you do have 3 ratios to compare, and again, decimals are pretty easy to do. But like I can check this one in my head without using my calculator because if your cross products are congruent or equal, and they are, right? 5 times 6 is 30, 3 times 10 is 30. That means this does give you 2 equivalent fractions. Or you could just reduce that second fraction, right? I know that both 10 and 6 are divisible by 2. So if I were to just reduce that fraction, it also gives me 5 over 3, and obviously that equals 5 over 3. So that's what the side angle side similarity theorem is. You can't just look at it and go, yep, that one's side angle side. You have to prove that they are by showing me that the 2 ratios are equal to each other, because sometimes they're going to give you some that are not, and you have to check that. So one last thing before I go, I do want to talk about how to, let me make sure I'm not getting ahead of myself. Yeah, how to find missing measurements. So this is my last example of how we're going to be using this just in regular triangles. I'm fairly certain you did this last year with Miss Lychuk. So you're going to be given 2 triangles. Oops. Again, I'm meaning these to look pretty, so just kind of bear with me here. Okay, so here I have 2 triangles. I'm given that, oh, wow, that is not, okay, so we're given that this angle is 94 degrees. And we're asked to find the measure of this angle. Ooh, is that right? I need some letters here. I do not like when they do this to my problem. Okay, so I'm going to add some stuff that they don't have. We're all good. It's all good. So I'm going to actually, let me do a little change in here. And so we're going to find this measurement. And this is L and P. And we know that this side is 20, this side is 24, this side is 35, this side is 42, this side is 21, and I'm looking for this side. And in the directions it will say something like triangle MNL is similar to triangle ONP. Okay, so that similarity statement is very important, just like it was with congruence. So you'd be given a diagram and be told that they're similar. And your job would be to find the missing measurements, in this case, angle P, which is 8 degrees, and side ML, which is, you can see where my X is. So since I know that they're similar, the first thing I know without doing any kind of work is that I know those angles are equal. I can see here that angle L corresponds with angle P, and the fact that they give me angle L is 94 degrees, I know that angle P, is also 94 degrees. So A equals 94 degrees. As far as the sides go, again, we have to use that concept of proportionality. So, like, is it equal? So obviously, I need to write a ratio comparing the one I'm looking for and the one that I have that it corresponds to. We know that, oh goodness, sorry about that, ML and OP correspond, right, because of our similarity statement. So I'm going to make that my first ratio, X over 21. From there, I can pick any other two that I happen to have a choice here. So I can see that, for example, MN is going to correspond to ON. So that's going to be my 20 and my 35. So I would have 20 over 35. Right? So what I end up with is, again, I'm comparing the sides using two ratios. It has to be equal because that's a proportion, because it tells me that it's similar. So my job is just to solve this little equation. It's really not that bad. If you remember from, gosh, we just did this with our 7th graders, so I know you've seen it before. When you're solving an equation, I can see here that I'm dividing by this 21, right? X over 21 means X divided by 21. So I'm going to multiply both sides by 21. So that's all I'm going to do. I'm going to do 20 over 35 times 21. So 20, and you get 12. 20 over 35 times 21. Again, these two divide out. You get 12. So that missing side is 12 units in length. Right? And please make sure your answer makes sense to the problem, right? You can see that the three on the left, how they compare in size, should compare, proportionally to the other three in size.